So now students, we will start with our next section in basics of semiconductor devices of ECD lab, and the next section will be your AC to DC or conversion. So here you can have the topic as AC to DC or conversion. Now in this, what we are going to do is you are going to convert alternating current into direct current. That is only called as AC to DC conversion. So when you are going to convert alternating current into direct current, it is converting AC to DC. Okay. Now here, if you see the nature of alternating current, you can see it like this. If you are having your electrical waveform, something of this type, it will be called as alternating current or alternating quantity. Okay. So this will be zero. This will be with respect to time, or you can have with respect to radians. This will be your amplitude. Okay. So this is your positive half cycle, negative half cycle, positive half cycle, negative half cycle. If you are having a quantity like this, so it will be called as alternating quantity. So if you are having a current which is alternating, so it can be called as alternating current AC. Now AC we have to convert to DC. So DC, if you look on the waveform, so you can see a pure DC will look like this. So this is your 0 point and this is some amplitude. Okay, so this will be your amplitude level. This is with respect to time or radians, anything you can take. Now this will be your DC, which is called as direct current. Okay, so you are going to convert AC to DC, and this conversion of AC to DC will be done by a circuit called as rectifier. A rectifier. Now this is very important, and because we have studied PN junction diode, the diode itself is going to act as a rectifier now. So in this rectifiers, you can have two types of rectifiers. One is called as half wave rectifier and another one is called as full wave rectifier. And in this section, we are going to see half wave rectifier in detail. Okay. Now, what are those terms and everything we will see. First, we'll see the contents, what we are going to see today. So first point, what we are going to see is why do we need a conversion of AC to DC? Now, whatever electric supply you get on your mains in your house or in your lab or in industry, anywhere you go, whatever you get electric supply on the main supply, that is alternating quantity, AC. Okay. And when we convert it to DC, it becomes a direct quantity. Okay. But why should we convert? Why? What is the need for a conversion from AC to DC? There are many electronic systems in today's life that we work on or we use on, which work on DC, and also the power or transmission lines. You know that power is transmitted from one point to another by wires. So if you transmit those power in terms of AC, it will have some losses. So it is good for transmitting the power in terms of DC. Okay, you can have motors which run on DC, small motors like DC motors. Okay, so there are many things, many appliances, many applications, many reasons why we have to convert AC to DC, and that is why the need for a conversion comes. Then second point, we'll see what is a rectifier, what is rectification. Third point, we'll see what is half wave and full wave rectification. Fourth point, we'll see what is half-wave rectifier. In that, we'll see what are the waveforms, efficiency, and ripple factor. And fifth point, we'll see what are the advantages and disadvantages of half-wave rectifier. And sixth point, we'll see what are the applications of half-wave rectifier. Okay, so let's start with the need. Why do we need AC to DC conversion? And for that, we will see a few points. Now, in that, the first point you can see for electronic devices or systems nowadays. Okay, so whatever electronic or devices or systems you are having, most of the electronic devices run on DC supply, and that is why we have to convert AC to DC. Say for example, You can't make a microprocessor run on 220 volt AC. You can't make a microcontroller run on 220 volt AC. You can't make any IC run on 220 volt AC. So that 220 volt AC should be converted to a lower voltage DC, and then only whatever appropriate voltage is required by the processor, by the microprocessor, by the integrated circuit, that only you have to give. That only you have to give. And once you give that appropriate voltage, then only the system is going to work. That system is not made to work for AC input. Okay, so your 220 volt AC which you get from your main plug at your houses or in your labs are not useful for electronic devices and systems. They should be converted to DC. So to convert that, you require a rectifier. Okay, then we'll see the second reason at a transmission level. Say whenever you want to transmit power at very large distances from source end, as DC transmission is having relatively lower losses than AC. Okay, so if you want to transmit AC power, so as compared to AC power, if you transmit DC power, if you convert that power into DC and then transmit, then it will have lower losses, because the losses can be of like skin effect, it can be effects of reactive power, it can be effect of instability. Okay, so all these losses will be minimized if you're having a DC transmission. Then we'll see the third point at domestic appliances, means the appliances what we use every day. Most of the devices which people use now are electronic ones, which must have DC supplied input. As I've told you earlier also, your mobile requires a DC supply. That is why there is a battery in the mobile. And because of that battery, it is going to get the DC supply. And whenever you charge from your AC point, you're charging only the battery gets charged, and to charge also the AC should be converted to DC by a internal rectifier, and then the battery will be charged, and whatever output the battery gives will be DC, and on that output your mobile is going to, that means your mobile is working on DC. Like that, there are many electronic domestic appliances, whatever you have today, which work on DC only. You might be thinking that whenever you are charging your mobile, you're putting the plug on the AC mains, but it is not like that. You're putting the plug into AC mains, that AC will be converted into DC, and with that DC, your battery will be charged. And that battery will store your DC charge, and it will give you the DC charge on which your mobile will work. So your mobile is going to work on DC, not on AC. Okay, so like that, there are many appliances, many electronic systems which work on DC, right? Then here the same point I've taken, to charge batteries. Okay, so there are many ways, means there are many types of batteries. Even your inverter will have a battery. Many things which work on battery. Now those batteries, if you want to charge, you have to have a DC. Okay, so it will be charged with DC. DC only can be stored in the battery. Okay, and once you have a battery format, once you have any appliance or any system with battery, then you can move that system, and moving of a system is called as portability. That point I have told in this. So you can just read the point here. AC supply can't charge the batteries because the average AC power at the end of one cycle means that is your positive and negative half cycle, is zero. So there is no net energy for the dumb electrolyte which is present in the batteries. As DC energy can be stored in batteries, so batteries require DC energy, and it gives also your output as DC energy. That is why whatever AC we have to convert it into DC, and for that you require rectifier circuit. Okay, now here the last sentence says that because you are having batteries, because the power required by the system is there in the battery, and you can take and move with your battery, it facilitates portability. Portability means you can move, like for example your cell phones or laptops. See, compared to your desktop or computer, your laptop, you can move because there you are having a battery which you can charge. Okay, then once you charge your battery, you can take that laptop and move anywhere because the power required by the system is given by the battery. Okay, but to charge a battery you require DC, and the battery output also will be a DC. Clear? Then we'll see another point for storing data. Now, you always see that memory is there in most of the electronic systems. Memory is there in your mobile phone also. Memory is there in your computers also. Now, whenever data is stored into memory, it is stored into DC format. AC cannot be stored. Okay, and that is why every time we have to convert AC into DC. So if you see this point, AC signals cannot be stored and DC power or signals can be stored. Thus, to store the electrical energy, we need to convert it into DC. Clear? Then we'll go to say another point which is related with DC motors. As DC series motors provide high starting torque, that is the bending force which start a motor, okay, and the DC shunt motor provides constant speed drives. AC needs to be converted into DC when and where applications of such motors are required. So there are many applications which are based on DC motors. They are light in weight. They work on DC supply. They can rotate on both the directions by changing the polarity. Okay, they are used in many electronic systems, and this DC motors require DC supply. And for to get this DC supply, your AC from the mains have to be converted into DC, and that is why we use circuits like rectifier to convert AC to DC. So these were some points. Then we'll see what do we mean by rectification. Now, rectification in an easy language, it means that a conversion of AC to DC. If anybody asks you which is the circuit which converts AC to DC, then the circuit which converts AC to DC is a rectifier. A rectifier. Okay. Now, if there is the opposite question asked, the circuit which converts DC to AC is inverter, but the circuit which converts AC to DC is rectifier. Okay. So here, the process of a conversion of alternating current, that is AC, to direct current, DC, is called as rectification. Rectifiers are the circuits which convert AC to DC. Rectifiers can be made from diodes, in which we can have half-wave rectifier. In half-wave rectifier, we use only one diode, PN junction diode. And in full-wave rectifiers, depending upon which full wave, whether it is center tap or bridge type, we can use either two diodes or four diodes. So multiple diodes are used in full-wave rectifiers, and a single diode is used in half-wave rectifier. Okay. So basically here you have understood now what is rectification. Rectification is the process of converting alternating current to direct current, that is AC to DC. And rectifiers are the circuit which will convert AC to DC. Then we will go to see the full wave rectification and half wave rectification, what it is. So here in this figure, I have shown you the a comparison of full wave. So here this column is shown for full wave. This is for full wave rectification, and this column is for half wave rectification. Okay, so here the circuit, if you go to see the first point, which is the circuit configuration, you can see here you are having a AC supply, and the full wave circuit here we have shown of four diodes. So diode 1, diode 2, diode 3, diode 4, and the output goes through a capacitor. Across a capacitor you are having the load, so that a pure DC reaches the output. Now here, this is your full wave rectification where you are using a diode more than one. Okay, so if you use two diodes or four diodes, you are building a circuit of full wave rectification. And this is an example of bridge full wave rectifier circuit. So similarly for half wave rectifier, you can see here only one diode is used, and this is your AC supply. At the output across the load you are having a capacitor, and then you are having this load. Okay, so this load is there. So across the load we are having a capacitor, because a capacitor will act as a filter But here, the main conversion from AC to DC is done by this diode in a half-wave rectifier and by this bridge in full-wave rectifier. Okay. Now, what will be the input for both the circuits? The input will be same. So the input waveform, if you see, it will be same: positive half cycle, negative half cycle, positive half cycle. Again, you have negative half cycle. You can go here also. You can have same input: positive half cycle, negative half cycle, positive half cycle. Again, you can have a negative half cycle here. So here you can have a negative half cycle. So it is an alternating quantity. So this input is alternating current, and this input also is your alternating current. So both the rectifiers, whether it is half wave or full wave, the inputs which you give will be a alternating quantity. Now the output differs. The voltage waveform after rectification, that is this point, if you see, for full wave rectifier, let the input be any half cycle, whether it is positive half cycle or negative half cycle, the output will be positive half cycle only. The output will be positive half cycle. So if you take for positive half cycle, the output is positive half cycle. Even if you take the input as negative half cycle, the output will be positive half cycle. Again, it will be a positive half cycle. Again, for the next negative half cycle, you can have a positive half cycle only as the output. So output is in one direction only. It is not going positive, negative, positive, negative. It is in one direction only, and it is giving output for any input. Means any input means whether the input is positive half cycle, also you will get positive output. If the input is negative half cycle, also you are getting negative. So for the full wave, that is, this is one positive half cycle and one negative half cycle, is called as full wave. So full wave is rectified. Full wave is converted into one direction current, unidirection current. Okay. So it is not that only half the wave we are converting, we are converting full wave. So it is called as full wave rectifier. So similarly, if you see in a half wave rectifier, if the input is positive half cycle, the output here is positive. The output here is positive. But when the input is negative half cycle, there is no output. There is no output here. Again, when the input is positive half cycle, it is positive. Again, when the input is negative half cycle, there is no output. So this rectifier, that is half wave, will work only when the input is positive half cycle. And when the input is negative half cycle, the diode will not conduct. It is not going to give you output. So there will be no output current in case of negative input. Okay. That is because it is working only for the half of the input cycle. That is, one cycle means positive half cycle, negative half cycle both. Because it is working only for positive half cycle, that means the output is working only for half cycle. So it is named as half wave rectifier. And here also you can see the output is only positive half cycles. There is no negative output. So that is also unidirectional. So here also in full wave also you get a DC output, and in half wave also you get a DC output. Okay. But this DC which are shown as outputs for full wave and half wave. Now this DC here, this DC here, and this DC here are not pure DC. They are called as pulsating DC. Pulsating DC means that DC will consist of some AC component in itself. Okay, so to make that pulsating DC into pure DC, we require filters. Now that a capacitor which we have shown in the circuit on both sides, here you can see a capacitor, here also you can see a capacitor across the load, that will filter out the AC components and it will pass only the DC to the load. So it is acting as a filter. So if you pass this output through the filter, then you can get a smoothing output somewhat like this, which can come near to the pure DC. This can come near to pure DC. Okay, even here you can see if you pass this through a capacitor, you are coming near to pure DC. Okay, so pure DC will be actually a ideal DC will be a straight line, but you can come near to that by having this type of filters. Okay, so output of rectifier is a pulsating DC, and that DC, if you want to convert into pure DC, you have to use a filter. Then we will go to see what is half-wave rectifier, because in this section we have to see what is half-wave rectifier, waveform of half-wave rectifier, efficiency of half-wave rectifier, and ripple factor of half-wave rectifier. So we are concentrating here on a half-wave rectifier, and also the experiment what you will do in the lab will be on half-wave rectifier. So in the lab also you have to obtain the waveforms, you have to see the ripple factor, you have to see the efficiency. Okay. So here, now what exactly we have told up till now about half-wave rectifier. In half-wave rectifier, when the AC supply is applied at the input, that is the positive and negative half cycle. Positive half cycle appears across the load, whereas negative half cycle is suppressed. There is no output when the input is negative half cycle. This can be done by using a semiconductor p-n junction diode. A simple semiconductor diode can be used for this rectification. A diode allows the current to flow only in one direction. Okay, so that is when the input is positive half cycle, the diode will conduct, it will be forward biased. But when the input is negative half cycle, it is not going to conduct, it is reverse bias. Thus, the diode converts the AC voltage into DC voltage. This is what is the basic working of your half wave rectifier. Okay. Then what is full wave rectifier? In full wave rectification, when the AC supply is applied at the input during both the half cycles, that is positive as well as negative, a current flows through the load in the same direction. This can be achieved by using 2 or 4 crystal diodes. If you're using 2 diodes, you are getting a center tapped full wave rectifier. If you're using 4 diodes, you can have a full wave bridge rectifier. Okay, so there are 2 circuits which are used for full wave rectification. They are center tapped full wave rectifier and full wave bridge rectifier. Okay, so here what will happen is, let the input be anything, let the input be positive half cycle or negative half cycle, the output will be positive only. Okay, so for both the input, that is for the full cycle, you are going to get a rectification at the output. Then we will concentrate now on what is half wave rectifier. The name half wave rectifier itself states that the rectification is done only for half of the cycle. The AC signal is given through the input transformer, mostly a step down a transformer, because whenever we require a DC, we require it in a smaller magnitude. We don't require 230 volt or something like that. Your AC which you get from the main plug can be of 230 volt, but the DC whichever you want at the output, that will be of a lesser voltage. So first we have to bring down that AC, step it down to a lesser voltage by a transformer, and then use a rectifier to convert AC to DC. Okay, so mostly a step down or transformer is used in rectifier circuits so as to reduce the input voltage. So here, say for example, if your input voltage is 230 volt, okay, 230 volt, which will look like this. This will be your alternating current, which is 230 volt. Now this 230 volt, if I want to convert it into a down voltage, a less voltage, say around 10 volts, I want to convert. Okay, so this I want to convert into 10 volts, so the amplitude will be less here, 10 volt. Now this can be done by a transformer, a step down transformer. Now this 10 volt, if I want to convert it into DC, okay, so this will be your DC 0. This is the amplitude, this is the time, this is your DC. Then this a conversion of AC to DC is done by rectifier. Is done by rectifier. But before rectification, the main voltage what you get from the supply, from the mains, that you have to step down by a transformer. Okay, so first you have to use a transformer. A transformer will give you AC to AC output only, but it will step down or step up, or it will keep the voltage same, depending upon the number of turns, coils in the transformer. Okay. So then next you can see about half-wave rectifier. The input signal given to the transformer is passed through a p-n junction diode, which acts as a rectifier. This is what we are going to see. This diode converts the AC voltage into pulsating DC. We are going to call it as pulsating DC because it is not a pure DC. In that pulsating DC, we will have some AC component along with DC, so it is called as pulsating DC. Now this pulsating DC we will get only for the positive half cycles of the input. A load resistor is connected at the end of the circuit. This is circuit wise what we are speaking about half wave rectifier, and we will see that circuit. Okay, so here you can see that circuit. So here you can see that there is a supply voltage V shown. This is your alternating quantity supply, whatever V is shown here. and then there is a transformer, and then there is a diode, and then you see everything. So here you can see the supply voltage. So this is your AC supply alternating quantity, which will be looking like this: positive half cycle, negative half cycle, positive half cycle, negative half cycle. Okay, positive, negative, positive, negative. This is your alternating current, and that will pass through the primary of the transformer here. Now, primary, you can see there are many turns shown here. There are many turns shown here, and you can see that secondary is here. Secondary is having less number of turns, so this is a step down transformer. So say if your voltage is around input voltage was around 230 volt, okay, so that will be stepped down to say around 10 volts, okay, or 5 volts or 8 volts, anything more, or whatever is your requirement. Now that AC here will be passed through the DC, and the output here you will get only for the positive half cycles. Output you will get only for the positive half cycles. For negative half cycles, you will not get output, because for the positive half cycle, the diode anode will be positive with respect to cathode. It will be forward biased. So it will conduct, it will pass the current. But for negative half cycle, anode will be negative with respect to cathode. It will be reverse bias. So it will not pass the current. Okay, so whenever the input is positive half cycle, you will get output. Whenever the input is negative half cycle, there is no output. So output is only for positive half cycles, and the output is only unidirectional. That output you can pass through this load, and you can take the output voltage across the load resistor. Okay, this is how the half-wave rectifier circuit is going to work. Then you can see here with the waveforms I've shown, that is, you're having first your AC. So in this AC, you can see that you are having your positive half cycles, negative half cycles. So here you can see this is positive half cycle, this is negative half cycle, positive half cycle. Again, you can have a negative half cycle here. Okay, so that will be the input. That input will pass here through this coil, that is the primary of the transformer, and then it will develop a voltage that will be magnetically induced into the secondary of the transformer. So transformer works on the principle of mutual induction, you might be knowing, which you have studied in BEEE. Okay, then here the secondary of the transformer is having less number of coils. That means whatever voltage you are giving here, bigger voltage, that will be made small here. Okay, because there is less number of turns here. So it is a step down transformer. It is a step down transformer. Now that voltage is still AC. That voltage is still AC. This is alternating current that will pass through this diode. Now when it is passing through the diode, when the input is positive half cycle, you will get an output. But when the input is negative half cycle, there will be no output. Again, when the input is positive half cycle, there will be output. Okay, so here the when the input is positive half cycle, the anode of the diode will be positive with respect to cathode, and the diode will be forward biased. The diode will be forward biased. But when the input is negative half cycle, the anode will be negative with respect to cathode, and the diode will be reverse biased, in which there will be no flow of current. So only when it is forward biased, it is acting as a passing device which will pass the current. When it is reverse bias, it is not going to pass any current. So we see that the output here, we have shown only positive half cycles. So when the input is positive half cycle, you will get the output as positive half cycle. When the input is negative half cycle, there is no output here. So there is no output here, no output here. Again, when the input is positive half cycle, there is output here. Again, when the input is negative half cycle, there is no output. So this is how the output will be coming for half-wave rectifier. And in this output, you can see the output current is only positive. It is only in one direction. There is no negative cycle in the output. So we call it as unidirectional output, and that will be called as your pulsating DC output. Okay, pulsating because this DC is coming along with some AC components, so it is called as pulsating DC. Then again, the same circuit. So here, this circuit, you can see that in place of diode, we have shown something called as short circuit. In place of diode, we have shown short circuit. Now this diode will act as a short circuit when the input here is positive half cycle. When the input is positive half cycle, okay, the diode will be forward biased, and because it is forward biased, it is passing the current, it is acting as a short circuit, and you will get an output. Okay. Similarly, when the input is negative half cycle, so you can see here, when the input is negative half cycle, so here you can see the input is negative half cycle minus, at that time the diode will act as an open circuit or an open switch. Okay. So here you can see when the input is negative half cycle, okay, the current will pass from here, okay, and then here you see the diode which was placed here, it will go into reverse bias condition and it will act as a open circuit or open switch, and it will not pass any current. No current will be passed to the load here. Okay, so output will be zero in case of negative half cycle input. So if you see the waveforms of half-wave rectifier, because in your syllabus he has asked about the waveforms specifically. Now this will be your input waveform which we have shown first. So here you can see your input waveform, and this will be your output waveform for half-wave rectifier. So input, you can see it is going positive half cycle, negative half cycle, positive half cycle, negative half cycle, positive half cycle, negative half cycle. Okay, so this axis you see that we have named it as omega t. This is in terms of radians. This is in terms of radians. This can be also in terms of time also. You can put this in terms of time also. Okay. Now in radians, you see that the first half cycle ends at pi. Pi is nothing but in degrees, it is 180 degree. Then the second half cycle ends at 2 pi. 2 pi is nothing but 360 degree. Like that it goes on. Okay. So a half cycle will take a 0 to 180 degree, that is pi, and the next half cycle takes 180 degree to 360 degree, that is still 2 pi. And this one positive half cycle and one negative half cycle complete makes a cycle. This is one complete cycle. Okay, this is one complete cycle which will give you the time period t. And if you know the time period t, 1 upon t will give you the frequency, and you can understand what is the frequency of the input. Okay, so those all terms you were expected to study in your basic electrical subject. Okay, then as far as the waveforms of half-wave rectifier is concerned, you can see that whenever the input is positive half cycle, the output is there. The diode is going to conduct. It will be forward bias. The diode is going to conduct. This diode is going to conduct. It will be forward biased. Whenever the input is negative half cycle, the anode of the diode will be more negative than the cathode. So the diode will be, okay, diode will be reverse bias, and therefore there will be no current flowing and no output you will get here. So no output here when the input is negative half cycle. Similarly, when the input is positive half cycle, the diode will be forward biased. Diode will be forward biased. You will get an output, okay, positive half cycle. And whenever the input is negative half cycle, the diode will be reverse bias. So it will not conduct. So no output here. So now output here. Similarly, here you can see when the input is positive half cycle, there is a positive output. When the input is negative half cycle, there is a no output here. Okay, so whenever the input is positive half cycle, the diode will be forward biased and it will conduct for that full time period from 0 to pi. That is for the complete half cycle, because your anode will be positive with respect to cathode for the diode. It will be forward biased and you will get an output. But when the input is negative half cycle, your anode will be not positive with respect to cathode. It will be negative with respect to a cathode, and therefore the diode will not conduct. It will be in reverse bias, and there will be no output at the output of the half-wave rectifier. So these are the waveforms of half-wave rectifier, which you have to show in the lab. Okay, when you conduct this experiment, you can show this waveform on the cathode ray oscilloscope, that is CRO. Then we'll go to see the terms like ripple factor and efficiency of half-wave rectifier. First, we will see ripple factor. Okay, now ripple factor will come into picture because ripple means the AC component which is present in the output of rectifier. Now, output of rectifier we are expecting to be DC, but that DC will not be a pure DC. In that DC, some component of AC will be there, and that AC component present in the output of DC for rectifier is called as ripple. And then we can calculate this ripple factor. Okay. Now, ripple factor is given in terms of RMS value of AC component to RMS value of DC component. It is the definition where you can say our ripple factor is the ratio of RMS value of AC component to RMS value of DC component. So here you can see if you want in terms of a current, then you can say that ripple factor here, ripple factor, which is represented by gamma here, can be taken as under root. This is under root. You have IRMS whole square minus IDC whole square upon IDC. If you take this ratio, you're finding the ripple factor whenever you know the IRMS current, IDC current. Okay. Say, for example, if you know VRMS, that is voltages, then you can take this formula. You can have VRMS square minus VDC square, which is under root, okay, upon VDC. This will also give you the ripple factor. Okay. So there are two formulas. One is based on the RMS and DC current, and one is based on the RMS and DC voltage. Now, these formulas we will use for half-wave rectifier, and we will see how much will be the ripple factor. That is, how much will be the AC component present. Okay. So here you can see a ripple factor is the ratio of RMS of AC component to the RMS of DC component in rectified output. That is at the output of the rectifier. When you say the output is a pulsating DC, in that if you take a ratio of the root mean square value to the DC, that is the average value, whether it is current or voltage, you can find out the ripple factor. So by IRMS and IDC, we can find the ripple factor of the rectifier. So in our process here, when we are going to or derive the expression for ripple factor, we will take IRMS and IDC. First, we have to see what will be the equivalent of IRMS and IDC for half-wave rectifier, because we want ripple factor for half-wave rectifier. So here you can see a ripple factor for half-wave rectifier. For half-wave rectification, IRMS is given as Im by 2, where Im is the maximum current. So here you can see this expression. First you should know, that is root mean square current is given by maximum current upon 2, and the average current, that is IDC, is given as maximum current upon pi. Okay, now this is very important. This substitutions first you should do in the ripple factor formula what we saw for the current. Okay, so this will be your substitutions what you have to do. Now after substituting this in the ripple factor formula what we had seen here, so here you had seen this ripple factor formula. So in terms of a ripple factor for a current, it is given as IRMS square minus IDC square upon IDC. So the numerator is under root. So you can take the complete thing here. So here you can see, you can take the complete root and you can rearrange this equation. So here you can see, you can write the same equation as under root IRMS square minus IDC square upon IDC square if you take it inside the root, and the same thing you can write if you take it, you can write it like this. It can be as IRMS square upon IDC square minus IDC square upon IDC square. Okay, so IDC square will be 1, and here you will be having IRMS square upon IDC. So you can take this as IRMS square upon IDC square minus 1. Okay, so this also can be a rearranged formula. So here we will use that and we will substitute IRMS and IDC in terms of Im by 2 and Im by pi. So if you substitute that IDC and IRMS, so what we got in our earlier, after rearranging the equation, whatever we got was ripple factor was equal to under root square IRMS square upon IDC square minus 1. This is what we got after rearranging. Now, if you put IRMS as Im by 2, so here we have put Im by 2. And if you put IDC as Im by pi, so here we have put Im by pi, that is whole square minus 1. The value what you will get when Im will get a cancelled and pi you are going to take it as 3.14 or a 22 by 7 approximately, and the value what you will get will be 1.21. This is very important. Okay, 1.21 is the ripple factor. Okay, so the ripple factor is more in half-wave rectifier. So here you can see a ripple factor of half-wave rectifier is about 1.21 by the derivation. As per, you can see that output voltage has much more AC component in the DC output. Actually, we want a DC output for the half-wave rectifier, but the AC component present in the DC will be more. So the half-wave rectifier is ineffective in a conversion of AC to DC. It will convert AC to DC, but its DC at the output is having more of AC component, and the ripple factor is 1.21 for half-wave rectifier. Then we'll go for to see what is efficiency of half-wave rectifier. So here you can see our rectifier efficiency is basically defined as a ratio of DC power, whatever you get at the output, to the applied input AC power. So for a rectifier, you are applying input as AC, you are applying input as AC, and output you are going to consider it as DC. Okay, so here, if you are having this rectifier, okay, this is your rectifier, say, and you are applying AC power here, and you are going to get output as DC power. So if you take the ratio of DC power upon AC power, okay, AC power, that is output upon input, so this will give you efficiency. This is going to give you efficiency. So efficiency is equal to DC power upon AC power. So it is a ratio of DC power upon AC power. Now, what is DC power in rectifier, half-wave rectifier, and what is AC power in half-wave rectifier? And then we will take a ratio, and then we will find how much is the efficiency. So here you can see the efficiency is given as, this is the symbol for efficiency, okay, and it is given as DC output power upon input AC power. Okay, now IDC, that is the average current, we know that it is given as Im by pi for half-wave rectifier, and the DC output power will be, now power, we know that it is I square R. Power can be given as I square R, or it can be given as V square upon R, or it can be given as V into I. Okay, so we'll take the first formula of power, that is I square R. Now here with that formula, we'll find out what is the DC power. So if you see here the DC output power, it will be nothing but PDC is equal to I square DC into the load resistance RL. Now IDC is nothing but Im by pi, so it will be Im by pi whole square into RL. Okay. Similarly, if you calculate the AC power also will be your current square into the resistance. So here if you see PAC, it will be IRMS square, that is the input current square, multiplied by the forward resistance and the load resistance, forward resistance of the diode and the load resistance, RF plus RL, where RF is the diode resistance. So for half-wave rectifier, we know that IRMS is equal to Im by 2. So if you put Im by 2, then you will get PAC as Im by 2 whole square into RF plus RL. Okay. Then if you take that in the formula of efficiency is equal to DC output power upon AC input power. So if you put that in the formula, you will get here Im by pi whole square into RL upon Im by 2 whole square into RF plus RL. Okay, so if you get that, then here you can see, if you substitute everything correctly, and then if you see, if you take pi as 3.14, okay, so there you can get the output of this equation as this equation, that is 0.406 RL upon RF plus RL, and here you can take it as 0.406 upon 1 plus RF barrel. Okay. Now the efficiency will be maximum. Now this is something we are going to assume now. The efficiency will be maximum when the forward resistance, which is the practical resistance of the diode when it is working in forward bias, is negligible. It should be actually zero for ideal diode. So it should be negligible as compared to the load resistance. Therefore, if you make that RF as negligible, then the maximum rectifier of a maximum rectifier efficiency will come to a value called as 40.6%. This means 40.6% of the input, AC input, is converted into DC by the half-wave rectifier. So half-wave rectifier is converting less than half of the AC into DC. So the efficiency is less as compared to your full wave rectifier, because it is going to work only for positive half cycles input. It is not going to work for negative half cycle input. So it is working for half of the input cycle. So here the output, if you derive in terms of efficiency and if you see the percentage, it will be 40.6% of the input AC which you are going to convert into DC. So 40.6% means it is less than half. Okay. Then what are the advantages of half-wave rectifier? So the advantages are very simple. It is less in cost. It is having only one diode, so it is affordable. It the connections are simple. Its circuit is simple, simple connections. Number three, it is easy to use as the connections are very simple and it is having only one diode. Number four is number of components used are less. Now here again the number of diode is one, and overall the circuit uses very less number of components. If you see the disadvantages of half-wave rectifier, then we know that the AC component in the output DC, because it is called as a pulsating DC now, because there is AC component, the ripple production is more, that is the AC component is more in the output. You have harmonics are generated, that is the multiplied frequencies of the basic fundamental frequency, which are called as harmonics, are generated. Then filtering is required because the output is pulsating DC. You require a filter to make it a pure DC. Then four, the efficiency of rectification is very low. So you have seen that the efficiency is 40.6%. It is less than half. If the input is 100, the output is 40.6. So the efficiency is less than half of the input. Okay. So if you go to see lastly the applications of half-wave rectifier, they are used for rectification mainly, that is a conversion of AC to DC. Then second, you can use it in demodulation circuits whenever you go to study a communication. In a communication, you can see at the transmitter, you are going to modulate the a carrier, and at the receiver, you are going to demodulate a carrier. So in those demodulation circuits, you can use. And number three, you can also use it for a detection of the peak signal. Okay, so signal peak detection applications, whenever you have to detect the envelope of a waveform, whenever you have to detect the peak value of a waveform, in that case also you can use a diode. So these are some of the important use of half-wave rectifiers. Okay. Thank you, students.